Okay, so yesterday we left off having just talked about summation notation. We talked about what that sigma symbol means. Whenever you see a sigma, it means we're going to be adding up a list of things. We talked about the index of summation. Our summation variable tells us the first value that we're going to substitute in for the variable. And up on top of the sigma, that m, that tells us the last number that we're going to substitute in for our variable. And we're going to do all the whole numbers in between. And this is how we find a partial sum. So we're going to start with an example. All right. So we're going to find the sum of this sequence. First question. How many terms will we be adding? All right, so Pedro, you changed your answer from 4 to 3. Why did you change your answer?
The last number in the sequence is 4, but the first number is 1.
The first number is 1, so we're going to start by substituting in a 1 in the place of k. So here's where we're going to start. And we need to do every whole number in between there and where it's telling us to stop. So we need to substitute 1 in the place of k. What else are we going to need to substitute in the place of k? We're going to start by 2. What else? 3 and 4. We're going to make these 4 substitutions. So how many terms are we going to be adding up? 4 terms. So Pedro, I liked both of your answers when you said we're going to add 4 terms. Wait, no, we're going to add 3 because you subtracted those. When we start with 1, we are including that. So if the index starts at 1, like this one does, the number up on top tells us how many terms we're going to be adding all together. We will look at a couple examples where the index doesn't start at 1, and then we'll figure out how many terms we're adding up there as well. All right, so what is our rule that we're using? Yes. K squared times k minus 3. This is our rule for the sequence. This first one, we're going to put 1 in the place of k. So I'm going to have 1 squared times 1 minus 3. So this first term is what? -2. We're going to add that. And now I'm going to put 2 in the place of k. So I have 2 squared times 2 minus 3. What is this going to simplify to give me? Negative what? -4. I just couldn't hear you. Because we're going to have 4 times -1. So this adds to -4. And then we put 3 in the place of k, so 3 squared times 3 minus 3. How will this simplify? 0. And then the term that we're going to stop with, we're putting 4 in the place of k, so 4 squared times 4 minus 3, and this simplifies to what? 16. And then we're going to add all of those up. How much? 10. Oops. All right, so there's our sum, our first partial sum. I want to do a couple more examples like this. Where does our index start this time? Index starts with 0. So my first term, we're going to substitute 0 in the place of k. The last term, we'll substitute what in the place of k? 5. So how many terms are we going to be adding up all together? We're going to add 6 terms. So k equals 0. What else are we going to need? 1, 2, 3, 4, and 5. All right, I'd like you guys to find these terms by substituting in and then add them all together. What is our sum? 189. 189. We have 3 for our first term, 6 for our second term, 12 for our third term, 24, 48, and 96. Oops. For a grand total of 189. All right. Before I put the next example up, do you guys have any questions for me? Cool. Let's do our next example. How many terms?
7.
7 terms. What are the terms that we are adding up here? What's the first one that we're going to have? What'd you say? 2. What will be the second term? 5. And then? 8. 11. 14. 17. And we will stop with 20. When we add all those up, 77. Conceptually, this is as hard as this part gets. Now, the function rules might be complicated sometimes, but the overall concept of we're finding these terms in a sequence and then adding them all together, are we okay with that so far? All right, let's look at one where the rule looks easy, but the sum is challenging. This is our last example in 10.1. We're going to start by substituting in 1 in the place of k. We're going to stop with which one? Stop with 6. So we're adding up how many terms total? 6. What will the first term be? 3 over 2. We're going to add that to what? 1, because it is what? 3 over 3. I'm going to go ahead and just leave it like this for right now. It does simplify to 1, you guys are right. What will the third term be? 3/4. The fourth term? 3/5. The fifth term? 1/2 or 3/6. And the last term? 3/7. I'm fine if you reduced those fractions down. We need to add these all up. Do you think a decimal approximation would suffice?
Yeah, I hope so.
Nope. We have discrete terms and we have the ability to keep it precise. What do I need in order to be able to add all these fractions together? I need a common denominator. How in the world can I find a common denominator for all of this? You said it's 140? So what would I multiply top and bottom by here to get 140? I know some of these can reduce, but I do want to go through the process of finding this common denominator because it's been a minute for some of us. Does that sound fair? Yeah. What things do I have to make sure to include if I need a common denominator? Does anybody know? Mixed numbers? Not necessarily mixed numbers. This common denominator has to be a multiple of 7. It has to be a multiple of 6. It has to be a multiple of 5. It has to be a multiple of every single denominator we have up here. So how can I find what that common denominator would have to be? Start multiplying stuff. Absolutely. What types of things do I need to make sure to include?
Denominators.
All of them? 7, 6, and 5 for sure. Three is a factor of 6. So I don't need to include the 3 because it's included here. What about the 2? Do I need to include a 2? Yes. Yes, I do. Because even though 2 is a factor of 6, what would I be leaving out if I didn't have another 2 right here? 4. It has to be divisible by 4. The only way it's divisible by 4 is if this number down here is divisible by 4. Here, I'm going to rewrite this 6 as a factor of prime numbers. 6 is what times what? 2 times 3. Will 7 go into that? Will 6 go into that? Yes, because I have 2 times 3. Will 5 go into that? 4? Yes, because I have what down there? 2 times 2. Will 3 go into that? Yes. Okay. When we're finding a common denominator, we want to look for all the prime numbers. Multiply your prime numbers together. What do you get if you multiply all those? $420. What's today?
420.
Aha. Look at me go. What do I need to multiply top and bottom by if I need a common denominator of 420?
So you get all of the common denominators, all of the factors, and you just multiply them together?
I need to make sure that I have every single factor represented.
So if it was like 8 up there, you have like a 4.
Well, if there was an 8 up here, I would need one more 2, because 2 times 2 times 2 would give me 8. If there was a 9 up there as a denominator, then I would need another 3, because 3 times 3 would give me that denominator. When you're writing down the stuff that'll give you your common denominator, you should be able to multiply, if you write them down as primes, you should be able to multiply or find your denominators in that list. Yes, ma'am?
Are we able to use calculators on this or no?
I need to double check. I do believe this is a no calculator section again, but I have to double check. I have to double check. Let me check and get back to you. What would I need to multiply top and bottom by if I need a common denominator of 420? 2 times what gives me 420?
140. Wait, sorry, not 140. 160.
210.
Oh my god.
'How'd you get that number off?
2 times what is 420?
Oh, never mind. I understand.
3 times what is 420? 140. 4 times what is 420? 105. 5 times what is 420? You said 80, 84. 6 times what is 420? 70. And 7 times what is 420? 60. So we have our common denominator of 420. So I have, what, 630 over 420 plus 420 over 420 plus 315 over 420 plus 252 over 420 plus 210 over 420 plus 180 over 420. Adding all of those together gives us what? I know the denominator already. That is what it will be after it reduces.
Do we have to do this in our head? Can you make a calculator?
What do you say, dear?
Can you make a calculator?
I can ask.
Shoot.
I can ask.
Can you show them this? Then ask them?
669 over 140 is what it would be fully reduced. I do know the yellow calculators, if you just type it in from the beginning, will reduce it for you. There's one more thing that I want to write down that's in this section. You do not have to memorize these. These are theorems on sums.
You said you don't have to write?
You do not have to memorize them.
Oh.
You do need to write them down.
Wait, why would you?
Theorems on sums. All right, so if I have a sum, or I'm taking one sequence, sequence A, and I'm adding it to another sequence, term for term, I'm adding them together, and then I want to add the whole thing together. You can find the sum for each sequence separately and add those totals together. Similarly, it works the same way for subtraction. You could find the sum for each sequence and then subtract those totals. And now the one that I think is the most useful. If you have some constant that is multiplied by each term in a sequence, and you want to find the sum,
What's the C?
that's a constant. Some constant number, something that's not changing with each term. You can find the sum of the sequence and then multiply by the constant instead of multiplying each term by the constant before you add them. You do not have to memorize these. They will make your life easier as you're working through stuff, but you can do it without these rules as well. All right. We are just going to begin touching on 10-2. We're going to shut it down a little bit early, but I do want to start 10-2 with you today. (10.2) is talking about arithmetic sequences. Do you want me to go back to that other one? Yeah, give me just 1 second. I'll go back. There you go. 10.2, arithmetic sequences. So here is the recursive definition for an arithmetic sequence. What does the recursive definition appear to be telling us? Specifically, what are you doing to get the next term?
Add something.
Add something to get the next term. We're going to be adding the same amount each time to find the next term in the sequence. What does that remind you of? If you keep adding the same thing each time,
Linear sequence.
it's like a linear function. So what's the difference between an arithmetic sequence and a linear function?
Different words.
Different words, yes, but there's another difference. We can graph that. You said you're not done yet? Or you are? Yeah. Are you finished? Yeah. Okay. We can graph this. What would it look like if we graphed a sequence? It's not going to be a horizontal line. Think about what we're allowed to use as input for a sequence. What are we allowed to have as input?
Numbers.
Numbers. What kind of numbers? Positive numbers. Integers. Positive whole numbers only are our domain. So just counting numbers, starting from 1. Do linear functions only have positive whole numbers as their domain?
No.
No, they have what?
Any number.
Any number. As long as it's a real number, any number. Decimals, fractions, negative numbers, doesn't matter. When you see a line graphed, that is an infinite number of little points all lined up. So close together that it just makes more sense to just draw a line connecting all those dots. What would it look like if I just graphed a sequence where the domain is only whole positive numbers?
It looks like
It's gonna be on like every line, like every corner.
Close. Very close.
well,
How do you
it would
graph a
be-
line?
It would only be in the first quadrant.
It would only be in the first quadrant. Why only the first quadrant?
Because it's only positive. And yeah, only positive.
You couldn't draw a line through it, could you?
You couldn't draw a line through it, no. It could be in the first or it could be in which other quadrant? It could be in the fourth quadrant because we can have negative outputs, but we can't have negative inputs. So if I couldn't draw a line through it, what would it look like?
Just dots.
Just dots. It's going to look like a scatter plot that appear to form a line, but they're not actually connected. Awesome. Okay, a sequence is an arithmetic sequence if there is a real number D for every K where K is a positive whole number, such that AK plus 1 is equal to AK plus D. The number D, which we can always find by taking any two consecutive terms and subtracting them. I want to find the difference between these two terms. This is called the common difference. The common difference in an arithmetic sequence is just like what in a linear function? The slope. Right. We're going to do just a couple examples of this, and then we're going to shut it down for today. So I'm going to give you an example of a sequence, and we're going to find the common difference, and then we're going to write a rule for the nth term. So here's our first sequence, -3, 2, 7, 12, and it goes on and on and on. What would our common difference be? What'd you say? 5. Okay. Then I want to write a rule for the nth term. If this is just like slope, how should we start it? You said what?
I said y equals.
Y equals. No, we don't have a y equals. What it equals will be the different numbers in our sequence for the different input values that we give it. How would you start this if we were writing a line? Y equals what? Positive 5. Because this is like our slope, right? If we were writing a linear function, it would be 5 what? 5x. We're going to use n as our input variable because we're writing a rule for the nth term. If I put 1 in there, will it give me the correct first term? If I put 1 in for n? No, if I put 1 in for n, it's going to give me what back? 5. But my first term is what? Negative 3. So how much of a difference is that? 8. Should I add or subtract 8 for it to give me the right output? Subtract. 5 minus 8 gives me negative 3. Would this give me the correct second term in my sequence? Yeah, because I put 2 in the place of n. That would give me 10 minus 8. Gives me an output of what? 2. If I put 3 in the place of n, what would it give me as the next term? 7. 15 minus 8 would give me an output of 7. For that minus 8 on the end, we're just going to have to use some logic, do a little bit of guess and check. Tomorrow we'll talk about a more algebraic approach to find that. I want to do one last example like this, and then we're done. So here's the next sequence. 17, 10, 3, negative 4, and it continues on. What is the common difference? Common difference is negative 7. So what would my rule be then? Negative 7n. What do I want the first term to be? I want it to be 17. If I put 1 in the place of n, which is what's supposed to tell me my first term, it doesn't give me 17. So what would I need to do so that it gives me the correct output? Plus or minus 24? Plus 24. Now would it give me the correct output? Would it give me this correct second term? If I put 2 in the place of n, it's going to give me 10 as my output. If I put 3 in the place of n, it would give me 3 as my output. We're going to stop here for today. Your homework over 10-1 is due tonight. Homework over 10-1 is due tonight. You guys have about 5 minutes if you have any questions to ask me about that or about what we were just going over.